Stable Diffusion 3 is now out. This is Stable Diffusion 3, and it looks really good. According to the samples they have here, according to the demo they kind of had on their website, and according to some of the early access some people have gotten, and it also can spell something Stable Diffusion hasn't been able to do before, which is quite cool, and they show why, which we'll see later. But yeah, quite cool, quite a cool model, and it's really a big step for open source diffusion. Hopefully this will stay around because stability is kind of having issues right now, but we'll see. Hopefully you can get your hands a hold of these weights, because this looks like quite a fun model to play around with. The theory behind it was also quite cool. The Stable Diffusion 1 came out. That was a big step with latent diffusion model, or with latent diffusion models. Stable Diffusion 2 was not very good, but Stable Diffusion 3 looks really, really good. So yeah. So let's get started with how diffusion and all that works. So a diffusion model, I'm going to go through it. I'm going to assume, so this model uses a transformer, and I'm going to assume a basic idea of a transformer. There's like a billion videos out there on how the transformer works, but basically just sequence to sequence. This is unlike a normal diffusion model, which uses a unit, and we're seeing everything go towards a transformer-based model as opposed to a unit model. Attention really is all you need, I guess. So yeah, let's get into it. So a diffusion model takes in an image. Let me draw my normal cat. So you got your cat like this. There, bigger ears. And we're going to call this x0. And this will be at time step 0. And I'm actually going to turn this into a interpolator, into a value between 0 and 1. But the time step can be arbitrarily large. Just normalize it. So this will be time step 0. And what you do is you take your image and you add a little bit of noise to it. Oops, wrong button. And so I'll add a little bit of noise to it, like so. And this will be x1, or rather, this will be x1 at time step, say, 0.1 or something like that. And then we take this image again, like so, and paste it. And we add a little bit more noise to this image, so it gets a little bit noisier. I don't know why I keep removing the bottom, like this. And say this is time step 0.2 or something like that. And you keep on doing this over and over again until you get to the last step, which is pure Gaussian noise. So this will be 100% noise and 0% signal. And this will be, say, x big T. And this will be our time step 1. So you basically have this chain from time step 0, which is 100% of your signal, x0, and time step 1, which is 100% of your noise, xt. To make this better, I'll call this 0.1, 0.2, and 1, just denoting it with the time step rather, so xt. I may also denote it zt, so that'll be the same thing. Z is usually used for latent, but anyways, you basically have your signal and you noise it to get 100% pure noise. And you can model this easily by an interpolation. We'll do 1 minus t times x0 plus t times epsilon, where epsilon is sampled from a normal distribution with mean 0 and 1 variance, so, or 1 standard deviation, whatever. So this is just a interpolation between your signal and your noise. Whenever t is equal to 0, so at the first step here, you have 100% of your signal and 0% of your noise, so xt is just equal to x0. Now, whenever t is equal to 1, you have 0% of your signal and 100% of your noise right here. So at t is equal to 1, you have x sub 1 is equal to epsilon. and at x0, you have that equal to, well, x0. Yeah, so this is basically the forward and backward process here. That's how we're going to model it. Now, the forward process is easy. You can easily do this. Just add noise to an image, subtract the signal. That preserves the variance. And you train a diffusion model to reverse this process. So we train a model. We'll call it m theta to reverse this process, like this. And given an image, what we do is we train the model to give us the noise in the image, all the noise. So we take in an image like this. We feed this through our model, say m theta, and the model will give us all the noise in the data. So if I remove all the cat, like this, then it will give us all the noise. So this is x sub t, and it'll give us epsilon. Or I should note that epsilon t. It'll give us epsilon t. And yeah, that's just all the noise. And what we can do is we can take xt and we can subtract epsilon t, and it'll give us x0. So yeah, this is the basic idea of it. You just want to train a model, some parameterized neural network that takes in an image and gives you all of the noise in the image. And then what you can do is you can just subtract the noise and it'll give you the original image. Now, one thing you may be wondering is, why do we have multiple parts of this chain? And that's because the prediction isn't going to be perfect. So there's going to be some error in it. And that's why we model it as this chain. So if it was a one-step process, we could just use like a GAN or something like that, which is one step. But the nice part about diffusion models is you have multiple steps. So it kind of refines itself. So instead of you taking this noise and directly subtracting it, what you do is you take the noise that it predicts, so epsilon t, and you subtract some part of it. So we'll call this alpha, epsilon t, and alpha is just some value between, say, 0 and 1. So you basically step in the direction of x0, but since you know there's going to be some error in epsilon t, you kind of step in the direction, but you don't completely take that step. So then you get x sub t minus 1, and then you make the prediction on that, rather. So the idea is you're kind of stepping in the direction of x0. Yeah, so this is the idea with m theta, and the way we train this, I think the idea of stepping towards x0 will make more sense in a sec whenever I kind of show it as an ODE. But first, I want to show how DDPM kind of did this. So this is kind of a discretized form here, but you can obviously make this a continuum if you have t in 0, 1. DDPM discretized it, so t was in 0 to 1,000, but it's the same with a continuum. Anyways, so DDPM essentially does this noise matching objective, the noise matching objective. So you have your loss, and you essentially just want to train your model to predict the noise. So your loss is equal to the mean squared error of your input here. So that would be xt, and the noise at that time step. I think it becomes evident what the model is actually doing, or rather it's m theta of xt and epsilon t. I think it becomes evident what the model is doing if I expand this term here. So m theta of, it would be 1 minus t of x0 plus t epsilon t and epsilon t here. So mean squared error between these two terms here. And all the model is doing is it's learning to remove the signal and just give you the noise, essentially. So given the time step, it just removes the signal from here. So it's a deterministic process. All the model's doing, just remove the signal. And equivalently, you may be wondering, oh, why doesn't it just remove the noise instead? That can also be done. Equivalently, you can have the model just predict the noise, and it gives you the signal. Because of how this is formulated, you can get the original image or the original noise and just subtract the two out. Here, or usually we just have the model predict the noise. So the model is essentially just removing all the signal from the image. So in this case, it just removes the cat from the image. And that's all the model's learning how to do. So that's what this objective is. Now, assuming we have a model that does this, we can easily get x0. So we just take this formula here, and assuming we have a model that learns a good function, we can, or a reasonable function, we can replace this epsilon t with, say, m theta of, well, we'll call epsilon hat t equal to m theta of xt. So we'll replace this with epsilon t, and we want to get the original image back out. We can do this by just rearranging the equation. So xt minus t epsilon hat t. So this is our prediction at this time step. So given this noisy interpolation, somewhere along this chain, our model is going to predict all the noise in the image. And what we want to do is we want to extract the original image. So I'm just going to rearrange this, 1 minus t x0, and then we get x0 is equal to xt minus t epsilon hat t over 1 minus t. So if we wanted to, we could do a one-step process where we just use this formula to get x0. That's kind of what's done in DDPM, but what you do is after you go to x0, you're like, okay, the model probably made a good estimate, but it probably has some error. So instead what we do is we take the previous time step, and the notation I have is going to be off from DDPM. This is just like a simplification, so it's not going to be exactly the same, but the idea is there. But anyways, you take your x0 and you add some noise back to it. So what we can do is we can take this, 1 minus t, and we can just add some noise back to it. So let me add a little bit of noise. Maybe we do, say, t minus 1. I guess that shouldn't be t minus 1. It should be t hat, something like that. So t hat times epsilon t hat, where t hat is one step less than t. So if t was equal to, say, 0.9, then t hat may be equal to 0.8 if you're taking 0.1 steps. So what this does is this term here takes our prediction and we subtract that from the interpolation we had. So this basically removes all the predicted noise, and then we move the model back to a step before. So you can think of this as if we are here, the model predicts all the noise, and we get something close to this image, but not quite. And you kind of move the model back a little bit, and then it predicts all the noise in here, and then you step forward again, going to what you think x0 was, and you keep on doing that. And you do that for multiple steps, and that's kind of the refinement procedure. And that's kind of what DDPM does. Now that was kind of the first version of this. What we do now is use ODEs and SDEs, and that was actually, I think that was before DDPM with Song. Dr. Song had his score-based models with SDEs and ODEs. And the idea behind that is you can use an SDE to get to go from your data distribution, so yeah, your data distribution, to some noise distribution. I don't have the picture on me right now, but essentially you can think of it like this. You have your data distribution X, and you have your noise distribution. We'll call it, this will be our Gaussian. And in the one-dimensional pixel case, so if you had a single pixel, it would be modeled like this. And let's say we have our pixel value here. So you can think of this as 0 to 255. Maybe this is our distribution over the data, and this is going to be our Gaussian here. And we basically have a stochastic that guides us towards a point on the Gaussian. So we have a stochastic, which basically increases in variance, or you can have the same variance, but it basically walks along this path to get to somewhere on the Gaussian. And this is going to be an SDE for the forward process. So we basically have our change in x is equal to, if I'm remembering this right, I think it's something like g of x and t times, I think it was just dt plus f of, I think it was also x and t, dw, which is the Wiener process or the Wiener process, however you want to call that. This is basically just the noise term. And this is a stochastic, and it just moves. It's basically an ODE, but you have your noise here, essentially saying, like, you know the direction you're moving, and the noise term just adds a little stochasticity to it. So instead of you going straight to some part of the Gaussian, you have this noise term which stochastically gets you to some part of the Gaussian. So that way it's random where you're going. And what you do is you use an ODE to go backward in time. So d of xt is equal to g of xt and dt. And it's actually some mess, and it uses score. And real quick, score, well, score is something else, but not going with the score, because I don't want to, or actually I can talk about score in a sec, but essentially you have your ODE here, and it is a straight trajectory back towards where you were. Once you've already observed the noise you wanted to, or once you've already observed the noise, you know exactly what noise to remove. And this is basically how it's formulated. Real quick, a side note on score. Instead of using this here, score basically, it's a side note, but a side note about score is if you have a model, say we have a model m theta, given an image, the model will basically predict a probability. And that probability is the probability of, say, that image existing. Say this will be like 0.1 because it's not an awesome picture. Maybe this is the best picture of a cat ever. And our model says this is, say, 0.99 or something like that. So this is the probability of just the image existing. Score is essentially the gradient of, well, it's essentially the gradient of this probability with respect to the input parameters, xt, or x, so with respect to our input image. So it's the gradient of the probability with respect to the input image. And you can essentially maximize that, use steepest ascent to maximize the score to produce a good-looking image. So say we're right here. What we can do is take the gradient of this image here with respect, or we can take the gradient of this value, the output probability, and we want to maximize that. So we take it with respect to the image, and we can change the pixel values to maximize this. So that's essentially what score is, if you've heard that before. And that kind of is what the original formulations were with the ODE and SDE. So I didn't actually talk about how, or the ODE perspective I was hoping to talk about. I guess I forgot when I was recording. I'm just stupid. Anyways, I'll do that now. So the idea is that you have this thing here, so x0, you have your image, well, I guess that would be x1, and you have your noise, x0. I guess it was flipped. So this is your image, this is your noise. So you essentially have this trajectory that you're modeling, and your model is going to be modeling that trajectory using this ODE. So ideally, if you had, so this would be your noise, this would be your data, ideally you would have a trajectory that would be straight. And this allows you to take a single step because it's a straight trajectory. Now, in reality, you're going to have like this curved area, the curved flows in this really high dimensional space. This is just a two-dimensional space. If you had 2 pixels in this really high dimensional space, you're going to have a lot of curvature. So perhaps your model will make a prediction, say, this way. And this is what the ODE predicts, your model predicts. And you can just take one step. So you could just take one step and you could go, say, all the way over here. Now, this isn't a good estimate, obviously. So instead, what you can do is you can just step along this a little bit and land in another spot. So this is the step size you're taking, and this is kind of the idea. So maybe now it predicts another trajectory. Let's say that. Now, let me move this. So this is our original, and let's say it predicts something like this. So if we did another just one step, then we would land here, which is a little closer, but it's still not quite right. And what we can do is we can just step along this again. So we take a step along it, and this is just like the good old Euler method. Just this is what the solvers do. They step along this trajectory, along this ODE, and this is basically the intuition behind why you can't just do one step and why it's nice to have multiple steps, allowing it to kind of correct itself. You basically step along this trajectory until you get to this point, and you keep on doing this over and over and over again until you reach this point here. And this curvature is what forces you to take multiple steps. If it was just straight, you could do one step. But yeah, this is the intuition I wanted to kind of give behind why you have to take multiple steps rather than just one straight step directly to the goal, or directly to the image, the full image. All right, back to me from like 30 minutes ago. Now, what this model does, Stable Diffusion 3 does, is it uses something called, let me pull it up. If I go down here, they use something called, where is it? There we go. So it's called, I think it was normalizing flows, rectified flow, that's it. So rectified flows are models that have been around, but they use the formulation to create a way to learn this ODE backward in time. Now, specifically, the ODE they want to learn is using this here. So this is the objective right here. And all this objective is you have a model here, v theta, and the model learns this, quote, velocity. Now, the formulation they set up is that you basically have this data distribution x, and you have your noise distribution over here, and you have your interpolation as we modeled it before here, where this is your signal and this is your noise, and you, instead of having 1 minus t and t, you have AT for your signal and BT for your noise. So this doesn't have to be a linear interpolation, though they do use a linear interpolation like I showed before. But it doesn't have to be. You can use different ones, but it's essentially like a straight path from your noise to your data. Or they make it a straight path for rectified flow. It doesn't have to be. It's a path from your data to your noise. Now, you can model this using velocity, and the velocity is just essentially how z changes with time. It's just the derivative of z with respect to time. So if you have, say, your data, x0, or rather x1, and you have your noise, say x0, which is equal to just your noise, 0, 1, and you have your trajectory, maybe it's a little curved, then, and this is going to be z here, zt is going to be somewhere along this trajectory. This can essentially give you your ODE here, which gives you your, basically your gradient here, or rather your derivative here, because it's with respect to time. So how does it change with respect to time? And that gives you this trajectory here. And you can basically take the derivative at a point, and then you can solve this using an ODE, essentially. So that's all this is. It's just the derivative of the velocity at a point, and you have your model learn that, or rather that's what u is, and you have your model learn the velocity. Now they formalize this using this objective here, and this objective looks like a mess, but it's not that bad. So I talked about this objective here earlier. This is just the noise matching objective. That's what we had before. So given the model, or given the interpolation at time t, the model predicts the noise in that interpolation here. So that's all it's doing. Learn how to remove the signal, give the noise. Now there's some extra terms here. WT is a weighing term. They mention down here that the resulting velocity prediction target is more difficult for t in the middle of between 0 and 1, because for t equal to 0, the optimal prediction is the mean of p1, and for t equal to 1, the optimal prediction is the mean of p0. So on your trajectory here, it is quite easy for the model to predict either completely on the left or completely on the right, because the prediction is quite easy. You either have all noise or you have all signal. So it's quite easy to make those predictions. It's difficult whenever you have somewhere in the middle. Somewhere in the middle of this trajectory is difficult because the model has basically both the signal and the noise, and it may be hard to distinguish between the two. So what this weighing term does, specifically how they use the weighing term, is they use this weight term to weigh the middle of the middle values of t higher. So whenever t is 0.5, wt is going to be higher rather than when t is equal to 0. So you place more importance on the model learning the middle of the trajectory rather than the tails. This term here and this term are used because they basically turn this objective here, which is the velocity matching objective, into the noise matching objective. And to do that, they need this term and this term here. So just some extra terms. Epsilon theta is also not exactly epsilon theta. It's this thing here. So that's just used to basically simplify this to a noise matching objective, which is quite easy to model rather than the velocity matching one. And then this here is just saying this is just the average over all your time steps uniformly sampled and over noise sampled from a Gaussian normal distribution. So yeah, that is rectified flows, and this is how they model it. They model it using this, and it's just noise matching, just a little fancier than usual. And like I said, they use a linear interpolation, which is the rectified flow. So this is what I showed before, and that's what they use. So anywhere is just a linear trajectory from the input to the noise. And the reason you need multiple steps to solve it is because you aren't going to get a perfectly straight, it's still going to be curved, a curved trajectory, because the model isn't going to learn a complete straight trajectory. If it did, you could solve it in one step. Since it does not, you have to use multiple steps to solve it still. So it would be desirable for the model to learn a completely straight trajectory, but in reality, it's not going to, because the space it's working in isn't nice. Now, to sample from a diffusion model, which I probably should have mentioned before, you essentially just take your input image here, or you take your input, which will just be pure noise, you send that through a diffusion model, and it'll output basically the noise at that time step. So this is Z0, and it'll output the noise, so it'll be something like, it'll be some mess like this. So if Z0 is sampled from our normal distribution, then it'll give something like this, perhaps. Maybe it is imperfect, some of the noise is removed, something like that. So it gives you something, and you just step in that direction like I showed earlier, where you basically just remove part of the noise. So then Z sub, actually this would be Z1. Yes, Z1. No, sorry, yeah, Z0. So then you step in the direction, so this would be, say, Z0.1, and you just remove a little bit of the noise using this prediction here. You then send that through the diffusion model again, and you keep on doing that until you get your output image. So eventually it'll remove enough of the noise. So all you do is sample some noise, send that through the diffusion model, and it'll output your image. So I forgot to mention that. Now, we actually don't work in pixel space here. We actually work in the latent space. And to do that, you just use a variational autoencoder or a normal autoencoder. Usually it's variational, and this is the thing Stable Diffusion 1 introduced. You take an image, say the cat here, and this will be an image of size L by W by your number of channels, say 3. So this will be L by W by 3. You send this through your encoder. So this is going to be our variation autoencoder. And if you're curious, Stable Diffusion 1, they talk, Stable Diffusion 1 it goes over all that, all about how this works, the encoder decoder. But yeah, essentially you just have this encoder, which encodes it to a latent space, and this has a large dimensionality. So we have a large number of channels, and it'll have, say, L over maybe 8 and W over 8. So it's a lot smaller. Actually, maybe we'll call this like 16 by 16. So I'll call it L over 8 and W over 8. So it's essentially this, it's the features of the image compressed into this latent space. And these will be our latents L. And this is what we're working with. We're not working with the pixels. We're working with the latents, and that's because it's a lot more computationally friendly. So you actually send this through the diffusion process. So you add noise to this, and then you turn it into, say, instead of it, so this would be like L1, this would be L0, and this will be our completely noised version of the latents. And then you train the model to reverse this, M theta, and it does it all in the latent space. And then what you do is you send this through the decoder once you're done working with it in the latent space, and it'll hopefully output your original image. These two things are trained individually. So the autoencoder is trained by itself. You just train this massive autoencoder on a ton of images, and then you train your diffusion model in the latent space once you're done. So you just transform these images into, you just encode the images and work in the latent space. So these are two independent processes, and you can find an autoencoder or a variation autoencoder kind of off the shelf, some open sourced one, and just make your diffusion model of that. So they're not trained at the same time, they're trained individually. So this is what we're working with, and later we'll see why. Yeah, so that's all about diffusion. One more thing I want to mention is clip. So if you've probably seen and heard of clip. Essentially what it does is it takes image text pairs and it wants to make them as similar as possible. It wants to make the embeddings similar if they're similar and dissimilar if they're not similar. So if I have an image of a cat doing the exact same image, I could draw a dog, but last time I did that, it was very scary. So image of a cat, and this will be, yeah, so we have image of a cat. Actually, I guess I could. No, I'm not drawing a picture of a dog. So you send this through your image encoder, and you also have the text corresponding to that. So this is a cat. I'll draw a tree. I'm not drawing a cat, or I'm not drawing a dog. Beautiful tree. And then you have the text for that. So this is a tree. There. So this will just be a batch size of 2 in this case. You then send these through the text encoder, and this will output your this. So this is just a transformer, and this will output your embeddings for each of these sequences. So in this case, so it'll be S by D, where S is equal to 4 in this case, because there's 4 words. It could be something else, but intuitively it could be 4. I'm gonna move this over. Now you have a separate image encoder, which is probably also a transformer because everything's a transformer. And this will also output so this one will correspond to this one here. This will output a sequence, say, we'll call this M actually. So M is the sequence length equal to 4, and this will be, say, N. Like this. So N, just to show that these can be different. You then send these through some reduction operation. So the reduction operation can take, say, the first token and treat this as a class token, or perhaps it does a mean over all the tokens or something like that. Anyways, it produces a vector representing this entire image here of size D. Specifically, it has to be the same dimension as these ones here. So these ones also get sent through a reduction operation. reduction, and they produce a vector as well. So this vector here would represent this sentence here, and this vector here would represent this sentence here. And these are also vectors of dimension d. Now what we do is we do this objective where we basically take the dot product, or we take the dot product between all the pairs of vectors. So you get these pairwise similarities here. So this first value here, I don't know why I drew it so big, would hopefully be large. You would want this to be quite large because this image corresponds to this caption here. Now this image here, the picture of the tree, and this caption here, you would want that to be a small value, say 0.1. And the same for the other two. This is a tree, does not correlate with this picture of a cat, so it should be the value should be small whenever you do the dot product similarity between these two vectors here. And the same for this one. This should be quite large because the tree corresponds to the caption. This is a tree. So you get this matrix here, and this is your contrastive. You can do a contrastive loss on this, and you essentially are going to have this matrix that's going to be batch size by batch size. Now, what you want to do is maximize the diagonal. So you basically want to maximize the similarity along the diagonal, and you minimize the similarity along the not on the diagonal. So we want to maximize these two here and minimize these two here. And that will give you, that's basically how you train Flip. And that'll give you a text encoder here and an image encoder where the outputs of the image and text encoders will be strongly correlated to each other. So if you have, so if you have the output of, if you have these two outputs, then these will be highly correlated, and these two will be not. They'll have a low similarity. So that's what you're looking for. And this basically gives you an image encoder that has text knowledge and a text encoder that has image knowledge. And we're going to be using this part here for Stable Diffusion 3. And this is what's usually used whenever you've heard of Clip. We don't want this because we're not trying to encode images, we're trying to encode text so that we can basically inject the model with textual knowledge. We also use T5, which is just basically a glorified BERT. And yeah, that's kind of the setup. A lot of setup, but cool model nonetheless. So yeah, let's go through this model. It looks quite simple. It actually isn't that bad. So to start, we take our caption. So the caption may be, I don't know, a cat on a rock or something. Some caption we want to encode. We then use multiple encoders to encode this information, and they specifically use this clip, and this T5, and all these output an intermediate representation. So if I go back here, these intermediate representations are what are immediately used. So pre-reduction, that's what we're using here. This is the pre-reduction information. So clip, the pre-reduction information goes here. The pre-reduction information goes here for this clip, and the pre-reduction T5 doesn't have a reduction, but it goes here because it's BERT, it doesn't have a reduction. So you essentially construct this matrix here where the outputs of clip are 77 tokens, and the output of T5 is also 77 tokens, and you concatenate them. And you concatenate them sequence-wise and dimension-wise. So you concatenate this one here, dimension-wise, with the other clip model. So you get this larger dimension here. Maybe this is like 2048 or something like that. And then you concatenate some padding. Maybe this is 2048 as well. So this will be 77 tokens by 2048 or by 4096 dimension. And then you concatenate this sequence-wise, which is 77 tokens by 4096 dimension-wise. And you just concatenate this and you get this big matrix representing 2 clip and 1 T5 encodings for the text. Now another thing they do is they get this pooled information here, And the pooled information is post-reduction for the clip models. Like I said, T5 doesn't have a reduction mechanism, and that's because it is a encoder transformer. So it doesn't have that reduction mechanism that the clip models have. That's not how it was trained. And the idea is that this will have fine-grained information, so a lot of information about more detailed information because you have more features, so it's going to hold a lot more information. The pooled has a lot less information, but it still carries information about the text info. So this is kind of like more lightweight information, while this is heavy this is heavy fine-grained information. And both these are going to be utilized. So this is going to be a vector of size n by e, say. So it's going to be just a vector here, and it's just concatenated the two features. So it's just a vector, a long vector, representing the text information representing the text information. This, on the other hand, is going to be a big, thick matrix of, what would that be, 154 by 4096, so 2 by 77 by d. And these are the two ways the text is encoded. This is sent through a linear layer, and this is sent through an MLP. The difference between the two is an MLP is multiple linear layers. You can think of this as like a linear layer projecting up, perhaps, and then a nonlinearity, and then another one projecting down. So your inverse bottleneck. Doesn't really matter. I think it's probably arbitrary. The next thing they have is this time step. So we basically want to tell the model where it is on the trajectory for the diffusion process. And the way you can do that is through these sinusoidal embeddings. So say we have this, and say we have some sinusoids with increasing frequency. So we have first sinusoid, second sinusoid, third, and they keep on increasing with frequency as you increase the number of sinusoids. Now imagine they repeat after some number of time steps, or after after so long. So basically, as your time increases, the number of sinusoids you have will repeat at some point. So it starts here and it'll repeat at some point because of the nature of sinusoidals. What we can do is we can say this is t is equal to 0 and this is t is equal to 1. And we can essentially just sample the sinusoids at any time step in between. And that can represent a unique positional encoding representing that time step. So say we had like t is equal to 0.5. We can sample along this line here, giving us, say, 0, 1, and 0, something like that. And that'll give us a vector of size 3 with the value 0, 1, 0, uniquely representing this time step here. And this is kind of a simplification a little bit. And what this does, and what we can do is we can inject this into the model, and this gives us a vector, which uniquely just represents the time step. And we can add more sinusoids, and we can add d sinusoids, which is the dimension here. So 4096, I think. Yeah, 4096. So we can have 4096 sinusoids of different frequencies, and that'll give us a unique representation for our time step. So that's all this is doing. Take the time step, which is a sinusoidal encoding, and then throw that through an MLP. And the funny thing is you just add this to your text information. So our y here is a vector representing text and time. This may seem weird, and it is weird. And they do this in Stable Diffusion XL. And I find it quite funny that you can just add this together, or you can just add these together. In Stable Diffusion XL, they also added information like, how do you crop this? How do you crop this image, and what? I think they also added a padding information or something like that. And they just added it to this vector here, and they just added a bunch of conditional information to it, and it worked well. It figured it out. The model could figure it all out from this one vector here. So it's quite interesting. You can just add a ton of information to this vector and it works. So this represents text and time, high-level text information and time. Now the final thing we need to do is add the latent information, which is probably the most important part. What they do is they take the image and they patchify it. And this is how you encode it. This is how you encode images into a transformer. And you can see that here, if we have an image here, you just take every patch and you flatten it. If you have, so we have an image here, let's break it up into 9 parts. And you also have the volumetric part here. You flatten the entire thing. So you take this and you flatten this entire thing. So the first pixel here, that one there, would correspond to, well, first we need to draw the vector, would correspond to this first pixel, or this first value in the vector. The second value, say you move over 1 to the right, would correspond to this next value. And you keep on doing that for all the values, and you do that for all the channels as well. So maybe this part represents the first channel, yeah, and this part, say, represents the second channel, and then this one represents, say, the third channel, so like RGB. And that's how you just encode that, and then you take the next one, and this will represent your second. This will be your second vector representing the second part of your image, and you just do this for your entire image. In the original VIT paper, they used 16 by 16 patches. Here, since we're in the latent space, we can use smaller patches. In this case, they do 2 by 2 patches because the latent space is so small. So the first part here represents a 2 by 2 patch. And yeah, it's a really small thing, but it also has the dimensionality to it. I'm not sure what the dimensionality is, but that's usually quite large. So it'll probably be larger than just 4 because this is the number of channels. But yeah, you essentially create this sequence of 2 by 2 patches. You then send this through a positional embedding layer, and that is just this here, except you sample unique sinusoids for each position in the image, and you can do that in a 2D way so that you get 2D information. And you just add that to the patches directly. So you add this 2D sinusoid positional information to the patches, and that gives you X, which is your latent representation. Now what we're going to do is we're going to send the text through the model and send the latents through the model, and they basically have their unique paths, and they're going to cross over sometimes. So you basically have a transformer for your text and a transformer for your latents, and they're going to cross over every now and then. And that's what this layer is here. So what we have is we have our text information, we have our latent information. So here, left is text, right is latents. And we start out with a layer norm. Layer norm just takes the statistics of the image, it makes the mean 0, and it makes the standard deviation 1. So all it does is it subtracts the mean and divides by the standard deviation. And it also has a learnable value, so the learnable value can change the mean and the standard deviation. So normal layer norm. Normal layer norm before you do anything else. Now, yeah, so this is basically just a big transformer, that's all. Now what we do is we want to take our text and time information, and we want to send it through 2 linear layers here. And instead of having a model, or instead of having an image with 0 mean standard deviation for the image, we can change that. So change the statistics using this text and time information. So we project it twice, once for alpha and once for beta. And alpha basically changes the variance and beta changes the mean. So it basically shifts the distribution by beta and scales it by alpha. And this is just the distribution representing the pixel values. Well, rather the pixel values and the text values. So you do that for both. And this part over here is just the same conditional information. So all you're doing is shifting or changing the statistics using this conditional information, the text, the text information and the time information. This has been done before. This idea where you change the statistics. I think the first time I saw it was in diffusion models beat GANs on image synthesis. And they use something called, I think it was ADA-GN or something like that. And essentially it did something similar, except this was a group norm rather than layer norm. But the idea was the same, where you took the input, you normalized it, 0 mean, 1 standard deviation, and you allowed this to change the statistics, which was the conditional information. Now you send this through a linear layer, which projects it to your queries, your keys, and your values. And you do this for both your the text information and the latent information. And yeah, so this would be the queries, the keys, and the values. And that's all your linear layer does. Now you have this normalization, which I'll talk about in a sec. But yeah, this normalization is quite important, but unlike a normal transformer. But anyways, you basically just you transform it into your queries, keys, and values. So this is when the information for the text information and the latent information are basically going to combine and mix together. So the sequences are concatenated together, like so. So if we basically have the two sequences, and this will be our text sequence. Oh, actually I have a diagram over here. So you have your text sequence here, which is 2 by 77. That's the sequence length by D. The dimensionality is the same, and you have your other sequence length here, which represents your image, which is also of dimensionality D. And you concatenate them along the sequence dimension, and then you send it through this attention mechanism. So the attention mechanism basically looks something like this. I'll draw it out over here. So you have your text part and you have your image part. So you have your sequence here, broken up into basically two parts, your text part and your image part. And this is your text part and your image part. So your similarity matrix is going to look like this, where this is basically going to be your text relationship. So if we just had a transformer by itself, modeling the text information, you would get this part here. Or other, you would almost get that part there because the softmax is across rows. So you almost, you kind of get that part. This down here is going to be the image relationships down here. And the off diagonal will be the other relationships. So this will be the text image relationships, and this will be the image text relationships. So these two here give you your cross information, the information flowing between the images and text. And yeah, this essentially allows text this still allows self-similarity between the text and text, the images and images, and it allows cross-similarity between the images and text and the text and images. So it allows mixing of information, but also information to be manipulated within the matrix, within the modalities themselves. So yeah, they just concatenate them, and then they do normal softmax attention. You then send this through two linear layers, and this essentially breaks up the matrices. So you split it, and you send it through the two linear layers, breaking up the modalities again, sending them on their respective paths. You then have this skip connection here, and yeah, that's just coming from up here, so a normal skip connection. And the way I think about this part here is this. So like we had up here, you had a scale and a shift. This here is essentially a scale value, which comes from your conditional information, and your shift value comes from your past or your skip connection. I think that's why they added this part here. This part's kind of weird, but that's the only reasoning I kind of had. Now we also have this layer norm here. So layer norm and then the conditional modulation, just like we had before, right here. So not any different. Then you have your MLP. So this is just your large inverse bottleneck where you have your vector, you then project it up. You have a nonlinearity, and then you project it down. You then have this scale and shift again, where this shift value is your skip connection. So yeah, that is the DIT block that they have. Basically two modalities flowing together and crossing via the attention mechanism. Now, there are some, so this is basically the model. This is the model, and the rectified flows are how they're doing the diffusion process. Now, there are a few more things I want to show. So specifically, they train this on an open source data set. So they train it on ImageNet and CC12M. So ImageNet, you may be thinking, doesn't have any captions, and CC12M is just some large, I think that's some large captioned data set. So they mention that they recaption the data, and they do that using, so they follow the approach and use an off-the-shelf state-of-the-art vision language model, CogVLM, to create synthetic annotations for the large-scale image dataset. And this was seen in the DALL-E 3 paper. You essentially want to recaption your data, at least somewhat, and it makes your data better, your model better, because the data is better. The original captions, apparently humans suck at captioning data, so recaptioning it is better. And you can caption the ImageNet data, and you can recaption CC12M to give you this 50-50 mix. And they show that the 50-50 mix has a higher success rate on, I think this was on the Gen Eval benchmark. So a higher success rate than the original captions, pretty much overall. Like, it's a pretty big margin. So if you're training a diffusion model, recaption your data. I guess that's a takeaway for this. Now, another thing is clip versus T5. So they mention down here. Yes, down here. So they mentioned that removing T5 has no effect on the aesthetic quality ratings, so there's 50% win rate, and only has a small impact on prompt adherence, whereas its contribution to the capabilities of generating written text are more significant. So T5 is basically needed to generate this good quality text, or at least it helps a lot, and it helps with prompt adherence. So you do need T5. It's quite useful, and they mention that down here, that T5 is quite useful in the model. It's not just this big block, a lot of computation that is useless. So T5 useful. Another thing they do is, let me see where this is at, right here. So in general, they pre-train the models on low resolution images, 256 squared. So they start off with just these 256 by 256 images, and they pre-train on that. And then they fine-tune the models on higher resolutions, as well as different aspect ratios. So you initially train with just 256 by 256 pixels, and then they fine-tune on larger images. And they change the embeddings, the time step embeddings accordingly. Now, another thing is this normalization they have. So I mentioned I was going to get back to this, and the normalization is quite important. If I go down here, so surprisingly, I think this first came from an Apple paper. At least that was the first time I saw it. At least a fix for it. The attention entropy, if you just leave it normal, so just with QKV, like normal projection, it has a problem where the entropy is all wacky. You basically want to stabilize that, and they mention they want to stabilize that because they mention it down here. But basically, whenever you're training in half precision, there's a problem whenever you have large sequences and you're training with half precision, and you run into an issue with divergence because of this attention entropy. And they mentioned they stabilize that using the RMS norm, and it stabilizes the attention entropy, allowing them to train using this half precision. So this is a very important thing that they add, and yeah, something that I thought was worth mentioning. That's why they have the RMS norm here, which you don't usually see in an attention mechanism. So one last thing, I suppose. I mean, if we look at here, they show that rectified flows are quite good compared to other variants of solvers. And they show that the model is quite good in general. Yeah, and they also show that it's better than UNet and normal VIT. So yeah, and it's also better to have, or it also doesn't do much if you add a third modality flow. So right now we have two. We have text and image. They basically had the idea for three sets where you have clip, T5, and image, and it doesn't do much better. So just use the two flows of text and image. I suppose the last thing is, and human preference is highly correlated with validation loss, which is always a good sign. And oh yeah, no, I think that was it. That's yeah. I mean, there's a ton of other results and stuff if you want to read about it. This paper is massive. I just kind of wanted to get the general ideas from it. Yeah, this is a massive paper. It's a really cool paper. It's really cool to see, and I'm looking forward to using it. I haven't used Stable Diffusion 3 yet, but I'm hoping I can soon. I think it looks really, really good. Anyways, yeah, that is Stable Diffusion 3.